Fine as well. As I said, today and tomorrow we're going to be looking at some what should be familiar terms that we've covered last chapter as well as early in the year. So just figure get those stuff out and ready. Be good to go. Now in today's discussion, we're going to come across a formula, but we don't need to actually use it mathematically. All we need to be able to do with it is utilize the location of the variables to help us justify our answers, okay? Again, no calculation. We're just going to use our noggins to solve an answer. So again, chapter 8, we are looking at the basics of chemical bonding. So there are three types of bonding that we're going to discuss in this chapter. The first one is ionic, okay? That is where we use the electrostatic attraction between ions. Again, that is not a new concept to us. Looking at covalent, the sharing of electrons. Again, that should not be a new concept to us either. Third one might be somewhat new, and that is metallic, where we have metal atoms bonded to several other atoms. Because of these unique type of metallic bonds, that's kind of what allows us to have electricity. So it's a very important one. About halfway through this chapter or so, we're going to look at something called Lewis symbols. They're also called Lewis dot structures or Lewis structures, a couple different names that they go by. And I don't think they're new to you. It all depends on really last year. We all know how well last year went. So it may pop out to you and look somewhat familiar. But what it is this gentleman by the name of G.N. Lewis pioneered the use of chemical symbols surrounded by dots that symbolize the valence electrons around an atom. So we all know what the valence electrons are. They're the electrons that are the outermost energy level. And so when we have compounds that form, the atoms tend to add or subtract electrons until they are surrounded by 8 valence electrons, the octet rule. So again, everyone's really trying to be just like the noble gases in terms of their electron arrangements, at least in their valence terms, okay? So far, other than maybe Lewis symbols, we've come across a few terms that we should know. We've talked about the octet rule, I know that. Now we're going to start off by talking about ionic bonding, okay? So in the last chapter, we saw that it takes 496 kilojoules per mole to remove an electron from sodium. Does anybody remember what that type of energy is called? Anybody remember? It's one of the first middle trends that we talked about. The energy that is required to remove electrons. I'll give you a hint. It rhymes with ionization energy. So it's going to be what? Ionization energy. Yes, I kind of did it in the voice of Scooby-Doo. Yes, the ionization energy is the energy is required to remove electrons from an atom. We look at other ways. Okay, if we look at chlorine. Okay, first we saw sodium in the last slide, now we're looking at chlorine. When we give chlorine atoms an electron so that they can have an octet, we actually get back 349 kilojoules per mole of energy, because when atoms receive electrons, it's an exothermic reaction. That's why the values are negative. Okay. Remember what that energy is called. Another hint. It rhymes with, I think I say it. Electron affinity. Electron affinity. I knew you'd get it. Yeah. So, electron affinity is, again, the energy associated with, or the energy change associated with atoms when they receive electrons. Okay. So, when we have an ionic bond forming, sodium likes to give up electrons, so it loses electrons, become a positive ion. Chlorine likes to gain electrons, so it has a negative charge. And so when those two ions come together, they form basically an ionic compound, metal, non-metal. And so we have a reaction occurring, but when the formation happens, is actually a pretty significant demonstration. So the numbers that are associated with sodium losing electrons, chlorine gaining electrons, does not yet explain why the reaction of sodium metal and chlorine gas is so exothermic when it forms sodium chloride. So there has to be, as I say, a third piece to the puzzle in ionic bonding. And so what has yet to be accounted for is that electrostatic attraction between the ions. And so once you use energy to remove an electron from sodium, and once you regain energy from adding an electron to chlorine, they now have an electrostatic attraction, like putting two magnets together. That's where the, oh, I got hair in my mouth, I'm gonna gag. Okay, sorry. So that's where this energy is coming from. Now, if you look up here on the board, what we have is some examples of Lewis structures or Lewis symbols, okay? Where we have sodium, we just use the symbol and represent it with a single dot because sodium is right over here in group 1. And chlorine is right over here in group 7. Sodium has 1 valence electrons, chlorine has 7 valence electrons. If you notice, during this whole process, since sodium loses 1, it's going to now have a full octet because it's now going to be dropped down to the previous energy level, and we're going to have 8 valence electrons, which is what it wants. Chlorine, by taking in the electron from sodium, now has 8 valence electrons as indicated by those dots. So they gave a name to this third piece of the puzzle, and they call it lattice energy. Okay. Now, in regards to why they call it lattice energy, when you have an ionic compound form, it forms this crystalline structure that represents a lattice. They're kind of stacked on top of each other, and they're kind of alternating. It's actually a very strong setup they have when they form these crystals. So what the lattice energy is, it's the energy required to completely separate a mole of solid ionic compound into its gaseous ions. And this energy that is associated with this electrostatic attraction is governed by what's called Coulomb's law. Now, this is the formula that I was mentioning that we don't have to worry about actually using it mathematically, okay? So what we're going to do is we're going to break this formula down and define what each of those variables is and what is really important to us in terms of our use, okay? So E, as we see here, is the potential energy of two interacting particles. And so the amount of E is going to be determined by the other variables. Oops. Q1 and Q2, which are in the numerator, those are simply just the charges on the two particles that are interacting. And so we're talking ionic charges. So +1, +2, -1, -2, so on and so forth. D, which is in the denominator of the formula, is the distance between their centers. So we can think about their bonding radius. Okay, we talked about bonding radius trends in last chapter. K, which is out here in front of both of those terms, is what's called a constant. It's there to allow for the calculation to occur. Again, for now, you don't need to worry about this number. Okay, that's not what we're really concerned about. What we really want to utilize are Q1, Q2, and D. Those are the only three variables that we're really going to worry about when we solve some questions related to this. And then when you calculate all that, you end up with the label of Coulomb, which is simply a measure of electric charge. Okay. So this slide right here gives us some very important information to help us solve problems. So we want to like highlight, star, whatever you need to do on this slide. Okay. Something we're going to refer to throughout this process. So we're talking lattice energy, and we'll be ranking various compounds in terms of their suspected lattice energy. So first, lattice energy increases with the charge on the ions. Basically, what that statement is saying is the bigger the charge is on the ions, the bigger the lattice energy. We have some ions that can be formed. We have some elements that can form ions that are really high in ionic charge. Then we have some that are just barely ions. Okay? So really one of the first thing you want to do is identify what the charges are. Okay? Because as we see on the bottom, charge trumps distance. Charge is more important in the long run than the distance between them. But if it comes down to a situation where we have to use the distance to help determine who has a larger lattice energy or vice versa, lattice energy increases with decreasing size of ions. So, simply putting that statement is the smaller they are, the greater the lattice energy. Because when you are a large ion, you have a great distance between your two nuclei. Okay? That means it's kind of like when you try to shake hands with somebody and they're really far away and you're reaching, compared to, you don't have to. If I was here with Mr. Jeffers and we shook hands, we can have a good bond. I'm trying to shake Ray's hand. Reach! Do it! See, we can't. It's not as strong. Okay? So the closer they are, or the smaller they are, the smaller the bonding atomic radius, the greater the lattice energy. Okay? So let's look at the question here. Now it might be a little difficult to see. There's a lot going on here. So we have the two formulas, sodium fluoride, cesium iodide, and calcium oxide. Okay. This is the first thing that we want to do. This is where we are reaching back to like chapter 2 or 3. It's been a long time. That's a very important concept that I was really trying to emphasize back then. We need to first identify the charges on each element in here. Since it is an ionic compound, we need to identify that. We're going to do that by their location on the periodic table. So let's look at sodium. Okay, sodium is what type of element? Metal, non-metal, metalloid. Sodium's over here. Element number 11. What is it? It is a metal. Very good. And therefore, fluorine is a non-metal. Good. Because again, ionic compounds are between metals and non-metals. So now we have to identify what their charges would be when they are ions. Sodium is in group 1. How many valence electrons does sodium have? Uno. Okay? Now, do metals form positive or negative ions? Cations or anions? Remember the word cation? What's hidden in that word? The plus sign. Metals form cations. So metals become positive. Can anybody take a guess as to what the charge on sodium would be? How many valence electrons does it have to get rid of? 1. So what do you think its charge is going to be? +1. I'm just going to write that up there. Now, when we have an ionic compound, the charges come together to form a neutral atom. So you can think about that, okay? We're going to kind of approach this a couple different ways to determine the charge on fluorine. So if we determine that sodium has a +1 charge, and an ionic compound is neutral, what do you think the charge on fluorine is going to be? -1. Another way we can approach that is, what group number is fluorine in on the periodic table? Seven. And what's that rule that we mentioned a few slides ago that everyone really likes to be, or really likes to obtain? Also sounds like an 8-legged animal in the ocean. The octet rule. So being in group 7, how many valence electrons does fluorine have? 7. So how many electrons? Well, first of all, is it going to lose electrons? No. It's 1 electron away from forming 8 valence electrons. So how many electrons is it going to take in? 1. Therefore, you get a -1 charge. Now let's try cesium iodide. Let's locate cesium iodide on the periodic table. Excuse me. Anybody find cesium? It's in group what number? 1. So what do you think is going to happen? Is it going to gain or lose electrons? It's going to lose. It's in group 1, the metal. How many electrons is it going to lose? 1. So what do you think its charge is going to be? Now when you look at iodine, again, you can use a couple different approaches. First one was knowing that ionic compounds are neutral. The second one was identifying its location on the periodic table to determine how many electrons it would need to gain. What group is it in? 7. How many electrons does it need? And therefore, it's going to be a what charge? -1. And the third one, I want you to determine what these charges are for calcium and oxygen. Okay? Anybody tell me what the charge for calcium would be? And why is that? It's in group 2. It's got 2 valence electrons. It's a metal. Metals give off electrons. Who wants to tell me what the charge on oxygen would be? -2. Very good. Again, looking at it as a neutral compound, got to have something that balances that. Secondly, oxygen's in group 6. It's a non-metal, therefore it needs to gain electrons. And since it's in group 6, it has 6 valence electrons, and it only needs 2 to form the octet. Bingo. Okay. So that needs to be your first step. First of all, we're going to take these 3 compounds and put them in increasing lattice energy. Okay? So the very first step in determining this type of question is find the charges. Assign the ionic charges to each element. It'll make your life easier. Next, once you've done that, you need to then go back to the previous slide. I'm going to come back to this slide. I just want to show you again. We're going to go back to the previous slide and look at that first bullet point. Lattice energy increases with charge on the ions. And so we're looking at Q1 and Q2, the numerator. Okay? And really, we're not worried about the signs. Okay? We're worried about the magnitude of the numbers. So if you were to look up here, and again, ignoring the signs, the plus and minuses, who would you say has the biggest overall charge? Who would you say? Who's got the bigger numbers? Yes, calcium and oxygen. Because if you think about it, the formula, Q1 times Q2, if we ignore the signs, we're going to have a much bigger product at the end. So calcium oxide is going to be the largest of the 3. Now let's look at the remaining 2. What's the issue with the remaining 2 compounds? And if you're to ignore the signs, what's the issue? Same numbers, therefore same magnitude of charge. Okay? So what do we have to look at next in order to help us determine this answer? What should we look at next? The size, the distance between the 2 nuclei. So the bonding atomic radius. Okay? The bonding atomic radius, as well as the ionic radius, which was the deal with ions, the trend is pretty much the same. Okay? So let's locate our elements again. Here is sodium, all right? Here is cesium. Can anybody tell me what happens to size as we go down a column? It increases. So, between sodium and cesium, who would you expect to be a larger ion? Cesium, very good. So keep that in the back of your mind. Now let's look at fluorine and iodine. Fluorine, iodine. That trend still applies to these. So which one would you expect to be larger? Fluorine or iodine? Iodine, yeah. So cesium and iodine were both larger in terms of their size compared to sodium and fluorine. But what do we say about size in lattice energy from the previous slide? Lattice energy increases with decreasing size. So the smaller you are, the greater the lattice energy. So since we identified that cesium iodide are larger ions than sodium and fluorine, who would you expect to have a greater lattice energy? Exactly. Sodium fluoride, since it is smaller, would have the greater lattice energy between itself and cesium iodide. So again, didn't use any math. Simply use the location of the variables, the trends on the periodic table that we've discussed, to help us solve this question. Now, you can betcha that we have another question very similar to this. And we also have another type of, when I say another type of formula, I mean, we're going to toss in some subscripts now, okay? So, we have MgF2, we have CaF2, and ZrO2. Magnesium fluoride, calcium fluoride, and zirconium oxide. Okay, now, before we start solving this, I just want to point something out. When it comes to, doing the Q1 and Q2, okay, for those, we don't have to worry about the subscripts. The only time we really have to worry about the subscripts or take them into consideration is when we are determining the charge for each ion, okay? So let's do the first one for example. Magnesium fluoride. Locate magnesium on the periodic table. How many valence electrons does magnesium have? 2. How many electrons does it want to lose? 2. So therefore, a single ion of magnesium is going to have what charge? +2, right? Now, we can use the formulas like we have before to give us hints about what a charge might be on a particular ion. Okay? We've already determined what the charge on fluorine was, and what was that? What was it? Not -2, but -1. Yes. And so again, I'm not, even though there's 2 present, as indicated by that subscript, I don't need to worry about that here. I'm just looking at a single ion. About calcium. I just saw it in the previous example. What is calcium's charge? +2. And we already know this is -1. Now comes the one where we got to kind of think. Okay? We have to think that ionic compounds are electrostatically neutral. So we have to use a little backdoor intelligence here. Okay? That might tell me, again, we're not worried about this. We actually, in this case, we have to use the 2 just to help us solve for zirconium. What charge do we give to oxygen for a single oxygen? -2. Okay? And I'm going to put that up here because that's what we're concerned about 1. But we need to figure out what is zirconium's charge. How many oxygens are present in this compound? Okay? So 2 oxygens present times the charge of -2. What would you get mathematically? So since there's 2 oxygens, in total, gives us a negative charge of 4. So, what would our charge on zirconium be? If we have a negative 4, and we have to balance the teeter-totter. Plus 4. And that's really the only time we would need to use the subscript in this case, is to determine the other ion's charge. Okay? So on here, we are asked this question not to place them in order, but to determine which one would have the greatest lattice energy. And our first thing we look at is what? Charge. Again, when we determine lattice energy, we can forget the signs. Who would you say has the greatest charge out of these 3? Very good. Zirconium oxide. It's got charges of 4 and 2. Those are pretty significant charges. Now, because I always enjoy kind of taking things a little further, let's identify which one would be larger of the remaining 2. So your answer for this question is zirconium oxide, ZrO2. But just to expand this, which one of these 2 would be larger in lattice energy? What's nice is, what do we notice about these 2 remaining compounds? They have fluorine. They both have fluorine. So really, we only need to compare their cations. So we have magnesium and calcium. Based off the trends, which one would be larger in size? Calcium is below magnesium. Therefore, which one would have the greater lattice energy between the 2? And the smaller you are, the greater lattice energy. So which one? Yes. Magnesium fluoride would have a greater lattice energy than calcium fluoride. Questions? I want you to kind of stew on this for a little bit today as the day goes on this evening. Come back if you have any questions tomorrow. Okay. We'll kind of wrap up section 2 tomorrow. And then once we're done with section 2, we'll call it a day on the notes.